All right, hello everyone. And in today's video, we are picking up from where we had left off in our discussions of random and systematic errors in measurement. And we are today focusing on how to represent them and how to identify those errors when plotting a graph, right? Because it's a very realistic scenario wherein when we are plotting graphs between two variables, then there will be some evidence or the other of random and systematic errors being displayed on the graph. So how do we understand that? So as we see over here, it's a pretty straightforward graph that we have over here. The solid dotted points represent the perfect results that we are supposed to get. So in general, say I have an equation of the form y equals to mx, or in this case, a equals to mb, where m represents the gradient. As we all know, for a relationship like this, the graph or the line of best fit for the graph should be a straight line passing through the origin as it is, right? Now, if there is systematic error in the data, as we see, the form of the graph does not change. This is the graph that represents that. There is systematic error in the results, and as a result of that, all the values are moved. They are shifted up by the same amount. This represents that's deviation, and that deviation is the systematic error. So we can identify the systematic error just by looking at this intercept that we are getting. So the intercept on a graph, which should be a line of best fit through the origin, gives us an idea of the systematic error or the magnitude of the systematic error that the graph is suffering from. Now, this is a pretty straightforward inference from what we saw. Now, as we see over here, just clear these out. Uh, One thing to note is that certain cases, the equation is actually of the form y equals to mx plus c, and the original equation itself has an intercept. So for that, the line of best fit will not be a straight line through the origin. The line of best fit will actually have an intercept. So it's very important for us to look at what kind of variables a and b are, and does the functional relationship between them necessitate the presence of an intercept. If it does, then it's not a systematic error. It is an intercept, and it represents the value of a when b is 0, or the initial value of a, maybe. All right. So that is a physical value that is important and significant in the analysis of the data. So we cannot treat that as a systematic error. But in all of the cases wherein, say, equation of this form is expected, but in reality we see an intercept being present, then that intercept will be the magnitude of the systematic error. All right. Now, apart from that, we see a few other points that I mentioned over here. The crosses represent the random error. So as we see over here, this is the perfect result that we are supposed to get. But because we know whenever we take measurements, because of the limitations of the measuring instruments or any fault in the method, there are cases wherein we get deviations from the perfect results. So these values actually represent those deviations. So that represents the random error. And pretty much the closer these are to this line, this perfect line, the less the random error is. So one way of finding out the random error is finding out the R square value, or as we call it, the variance in case of statistical data. It's very easily found. If you plot your graph on an Excel sheet, for which we will have another tutorial later, we will see that there is an R square value determined and displayed on the graph. If you all already are aware of how to plot a line of best fit on Excel, you can try it. Display R square value is shown on the Excel sheet. You can choose that option and it'll show you the R square value. So R square almost equal to 1 implies very low random error, and that means your results are very precise. All right. Now, please know that R square exactly equal to 1 is an overfit, and please don't choose a line of best fit that makes R square exactly equal to 1, because that might be mathematically correct, but not physically so. We have discussed that in the line of best fit series of videos where we viewed a simulation to show how we can choose a line of best fit to properly suit the needs of the data points, and how to arrive at a suitable set of or a suitable mathematical relationship using the line of best fit by looking at the R square values and also the spread of the data points on the plot. Now, as we see over here in these examples, uh, this one and this one, these both these diagrams, they showcase lines of best fit. So that again tells us that lines of best fit need not necessarily be linear. And by linear, I mean straight lines, because the name suggests line of best fit, and we subconsciously kind of relate line, the phrase or the word line, to always being straight, is a misconception that most people have. So lines of best fit need not be linear or straight. So they can be curved, they can be polynomial, depending on the way the data is arranged. So the best way to look at it is it should pass through all these crosses that we see over here. These crosses actually represent the error bars. So this vertical cross represents the uncertainty in quantity A, and the horizontal one represents the uncertainty in quantity B. So whatever measuring instruments you use to measure A, the uncertainty of that is found in the vertical one, and the horizontal one showcases the measuring uncertainty or calculating uncertainty of the value on the x-axis, or the quantity B in this case. So representing the error bars is something that you will have to practice and you will have to get used to, because like we saw, any kind of measurement is limited by the amount of uncertainty that is present in it during the measurement process, and you have to represent it on the graph as well. So the line of best fit, so actually it helps you see that the line of best fit in fact should pass through all the error bars, right? And in general, we take the bigger the error bar, the better the line of best fit in that sense. So we try to align the fact that it has to pass through all the error bars. We take the bigger of the two, and we consider the line of best fit if it passes through all the error bars of that bigger uncertainty range. Say if the vertical one is bigger than the horizontal, then we only consider the vertical error bars, and we draw the line of best fit, keeping it consistent with the vertical error bars and ensuring that all of them passes through the vertical error bars at least, right? And in certain cases like these, you will find that they're passing through both. So this is a perfect scenario. So those are things that you need to keep in mind. Whichever is the bigger error bar, you draw your line of best fit in correspondence with that, and you ensure that line of best fit passes through all the error bars of that bigger error bar set. Okay, so now before we move on to another discussion, this is a very important thing. I'm pretty sure I cannot sufficiently emphasize upon the need for you to be very careful regarding finding out the gradient of the line of best fit. You have to draw the triangle as big as you possibly can, and not take experimental data points while you are considering them. Another thing that most people have problems with is the area. The area under the graph, like say if I have a graph like this, this shaded region represents the area under the graph. So this can equally mean something. Like say for instance, the easiest way to determine what this can determine is looking at what these y and x values represent. In general, if this represents say mass and this represents say acceleration, then we automatically know mass into acceleration would give me some sort of a force. So this gives me a measure of the force acting on the system. If this represents say velocity, this represents time, then we automatically know velocity into time should give me displacement, right? So it's very important for us uh, to be able to look at these axes and what values are represented on these axes and multiply them, and the product of the units of these quantities that are represented on the axes, that will give me the value of the area. Similarly, you can actually use the same logic when you are finding out the gradient. You are using delta y by delta x. So in that case, we just find out what the quotient of the units of y and x represent. So if this is displacement, it'll be in meters. This is time, it'll be in seconds. So meter per second, which means the gradient will give you velocity or speed, depending on whether it's distance or time. All right. So these are two techniques that come in really handy when you are looking at an equation and trying to figure out what kind of a line of best fit it would form, and what would be its gradient and intercept uh, in a given situation. The gradient is given by whatever is there on the y-axis divided by whatever is there on the x-axis. Take their SI units and figure out what the gradient can represent. And if it's the area, then you just take a product of the SI units of what is there on the y and the x-axis and try and figure out what they might represent. More often than not, you'll arrive at the right answer. So be careful while handling those SI units. Now, finding out the area under the curve can be just because, say, for instance, this curve is not a proper geometrical shape. Okay, so finding out the area under this curve physically is a little difficult. So what we do is we have to count the squares. So you have the graph like this. So you have to, in fact, find out the value of a small square like this, and then end up counting all the squares that you have and making an estimate of the area. Multiply that number of square with the value of one small square to get the value of the area. More often than not, the IB allows you a given range within which your answer would be accepted. So there is no point trying to figure out what the exact count is. But do note that if there is 1/2 of the square over here, so you only take half a square and you don't take one full square. So those things are certain techniques that you will have to learn as you go, and we will discuss specific problems where you need to display these techniques and kind of apply them in assessment situations. So more on that later. But I would want you all to remember this in case you encounter this before we are able to address that in this course. So the next thing, all right, now we come to something that is also very important and a technique that we need to apply every now and then. It will be used by you while you do your IAs, while it will also hold importance when you are answering your theory questions. So what is this in fact? Of course, this is y, and x. So as you see, this is a line of best fit, the black line in between with all the points. Okay, so for simplicity, I've actually drawn all the points lying on the line of best fit. So let's consider it to be an ideal line of best fit, and with these error bars that are represented on them. So I've only taken vertical error bars. Please note that in certain cases you might come across errors that are uncertainties that are so small now they cannot be plotted on the graph. So in those cases, you can ignore them, especially while doing your experiments. You might be using very precise instruments like, say, the timer on the Logger Pro, right? Light gates. So they are extremely precise. So they have very, very small least counts. So the uncertainties in those time measurements will be extremely less. And you probably won't be able to plot them on your graph. So not to worry, you just need to mention that the error bars are so small that they can't be plotted on the graph without compromising on the reliability of the graph being plotted. So we see over here that this is the line of best fit. Now, this is a technique that we use in order to figure out the uncertainty in gradient and the uncertainty in intercept if applicable. So over here we see that, okay, C is the intercept we have. So our equation is y equals to mx plus c, which is the equation for the line of best fit. Okay, now as you see what we have done over here, the red line signifies another straight line which is connected to the maximum positive uncertainty of the last point on the data set, and the maximum negative uncertainty or the lowest point in the data set, which gives me a line of best, or a line of fit that is actually way steeper than the line of best fit. All right. Similarly, the blue line represents a line that is way flatter in terms of its gradient compared to the line of best fit. In fact, if you do a rigorous mathematical calculation over here and use proper graphical tools to plot the graphs, the angles that you see over here, right? The line of best fit is actually the angle bisector between these 2 points. So if you are able to draw a line of best fit, which is an angle bisector between these 2 lines, then your line of best fit is actually the best fit for the given data points that you have. Looking at it the other way around, right? So these 2 lines, the blue and the red ones, they call the lines of worst fit, and they help us figure out the uncertainty in the gradient and the intercept. So all that you need to do is you have to first find out the gradient over here. So you've got you draw a triangle and you find out the gradient of the line of best fit. Then you do the same thing, figure out the gradient of the line of worst fit, and this one as well. Okay, so let's call this M1, let's call this M2. So delta M is actually given by, the uncertainty in M is given by, obviously M1 is way greater than M2, so I can write M1 minus M2 by 2. So half the range of the possible fits corresponding to this data point, these set of data points. All right. So what you understand over here as the physical significance of these 2 lines is that they are the worst possible fits that you can plot using these set of data points. So this is the flattest line of worst fit. This is the steepest line of worst fit. You can think about it like that. And the line of best fit is somewhere between the 2 of them, in such that is going in such a manner that it acts as an angle bisector between these 2 lines. All right. So again, if I have this and I have that, so I'll have C2 and C1. So delta C will be given by C2 minus C1 by 2. So there you have the uncertainties in the gradient and the intercept of a line of best fit. So if you are given a graph, sometimes the IB does that. They give you a graph with the arrow bars. They want you to plot the line of best fit. After that, they want you to figure out the uncertainties in the gradient and the intercept. So this is how you do it. Now, remember that those of you who want the easy way out, you can also do something else. You can neglect one of the lines, in fact, and just figure out the difference between the best fit and one of the lines of worst fit, and that would also give you there is a similar and consistent result. So delta M can also be given as M1 minus M or M minus M2, and delta C can also be given as C2 minus C or C minus C1. So you can do with one line of worst fit and the line of best fit. All right. And just figure out the uncertainties in the gradient and the intercept based on that. Now, of course, you know the rules of how to find out the uncertainties. Always round off to the least SF, okay, for uncertainties. Okay, so your gradient might be in 3 SFs, but your uncertainty in gradient cannot be in 3 or 4 SFs. It should be rounded off to the least possible SF that is allowed by the experimental data. All right, so that is something that you need to keep in mind. Another thing that you need to sometimes help with is how to round off your answer. Say you have in your final result something, say C equals to A plus B. Okay, so how do you round off C? If this is say 2SF, this is say 3SF. Okay, so of course the answer is pretty simple. Just round off to the lowest possible SF. Now, keep in mind, what is A? Is A measured value or A a theoretical value? If A is a theoretical value, then no, you will round off to 3SF, which is the significant figures for B, because it's a measured value. So the rule is round off to the lowest SF slash DP, depending on how you want to keep it consistent, offered by a measured value in the problem. All right. Okay, then, so that's all for this video. I'll see you later in another video with another concept. So till then, happy hunting.